It is the last formal meeting of the course 4676. This is Introduction to Computational Chemistry course. The goal of the course is that students of broad background and broad background in level of advancement and in the primary subject area, chemistry, physics, biochemistry, engineering, polymers and coating, get exposure to the practical methods for computational chemistry research, so that skills acquired in this course can be accumulated towards the practical research of the attendees of this class. There was several background components, but last couple of weeks, everyone in this class was spending in doing research projects, applying their newly accumulated skills towards practical research of their interest. So the results of this research are very encouraging. They're seeds of serious research. But those who are guests, please take into account that 2-week research cannot be judged on the same level as professional research made for years. So main goal of this component, well, one of the goals of this component is to induce an appetite to computational research, so that those who are exposed in this course can continue going on if it looks interesting. Presentations are split onto 4 segments: the study of minerals, study of catalytic reactions, study of nanointerfaces, and study of charge transfer. The course itself was organized as a superposition of 3 things. One is theoretical background, another is practical skill, and third, scientific communications. We were spending time on learning equations, building atomic models, running correct software on a correct hardware, and computing observables related to your research interests. Right now, it is time to practice scientific communications, to make write-ups, to play reviewers, and now present and survive questions. So please be aware, we are still very limited in time. Please never overcome the 8 minutes per talk total. Out of this 8 minutes, 1 minute is to walk to the stage. So if you are feeling that you are spending more than, skip something and go to conclusions. We need to be in time. If guest reviewers have an opportunity to judge the talk, making marks near the level of presentation in several categories, like analysis, presentation, reasonable conclusions, and ask those questions that are not fit in 2-minute section for answering questions. So if there will be no questions, bad. If questions will be going too long, also bad. So please try to limit questions, and if you really want to ask the presenter, just write down near the name. With this, I would like to show you the protocol, how we do these presentations. All of your presentations are uploaded to this computer. They are numbered according to the number of presenter and named according to the name of the presenter. So you're browsing to the right presentation. Click on it and bring it to the big screen. This, I would like to announce first presenter. HM Nasrullah Faisal, who will show the application of computational chemistry methods to description of optical properties of minerals. Okay? Stage is yours for generous 4 minutes.
Hi everyone, good afternoon. This is HM Rasulullah Faisal. The topic of my today's presentation is WASP simulation of calcite mineral. Actually, calcite is one of the most predominant geological minerals on Earth. Actually, it is a stable form of calcium carbonate that is found on sedimentary rocks. In global carbon cycling, contaminant transport, local pH and alkalinity of terrestrial environments, calcite has some contribution. In nature, it is also often found in doped forms with different metal ions. Actually, this is the unit cell of calcite. The unit cell of calcite is hexagonal and the space group is R3C. In the stoichiometric unit cell structure, the value of Z will be 6, so there will be 6 carbon atoms, 6 calcium atoms and 18 oxygen atoms. Here we build our optimized structure for the MD simulation of calcite. The Vienna ab initio simulation package is a computer program for atomic scale materials modeling, like electronic structure calculation. It computes an approximate solution by using DFT or Hartree-Fock or a combination of both. After optimizing our structure, we run MD on different temperatures like 300 Kelvin, 600, 850, 1000 Kelvin and 1500 Kelvin. Then we thermally optimize the structures and import different properties of them. So first, the density of states. Actually, it indicates the number of states per interval of energy at each energy level that are available to be occupied. Here, this is the DOS diagram of our geometrically optimized structure. And after running MD at different temperatures, we got this DOS diagram. So if we look carefully to this DOS diagram, you'll find that with the increment of the energy, the homology gap is decreasing. But up to 600, up to 800 Kelvin, we cannot find such significant change in the gap, but from the 1000 Kelvin, we can find the significant gap between HOMO and LUMO. Because the thermal decomposition of calcite completes about at 900 Kelvin, so after that, if the MD is done, you can find the significant HOMO-LUMO gap. And if you do the MD on higher temperatures, that energy gap is supposed to be decreased. Now the absorbance spectra. Actually, it is the light matter interaction. So if you look, this is the absorbance spectra of our optimized calcite. The peak is in the UV region. If we, after doing the MD, if we look at our absorbance spectra, we look that there is not that significant change in the spectra, but the population distribution of the spectra is slowly moving towards the visible region. And if we do the MD at higher temperature, we hope that we can get the peak in the visible range, so that at that time we can get the color of the calcite. This is the MD of calcite at 1500 Kelvin. That's the video. Okay, so after that, we are inquiring the different properties of different doped calcite. One is the siderite. It is one of the most common doped forms of calcite. Where the one calcium ion is replaced by one iron. So if we look at that, this is our optimized structure. And then we also study the DOS diagrams. Here is the geometrically optimized DOS of our structure, and this is the thermally optimized. This is the DOS diagrams of the thermally optimized structure. So if you look at that, here the total number of orbitals that are contributed by the iron d orbitals should be 5 due to the for the singlet ones, and for 10 for the spin polarization, and also for the 630 Kelvin. And if you look at the absorbance spectra of the siderite, actually the most important thing is to do here, we should do the spin polarization for that, and I have a plan. I will do it in future. But for this absorbance spectra, we can assume that here the iron is in the high spin, or it may be possible that the crystal field splitting is very far from the ideal or high symmetry. Here the iron d orbitals are offset from each other instead of forming a region. And we can also see that here the iron orbitals are hybridized with the host orbitals. This is the MD of siderite at 630 Kelvin. And that's another form of the doped calcite. It is rhodochrosite, and we did the simulation at 630K and 750K Kelvin. And if we look at the density of states orbit DOS diagram, we can also find out that here the homolume energy gap is also increased with the increment of the temperature. And if we look at the absorbance spectra, we can find that the orbitals are separated into two regions here, and the DD transition is less intensive or almost vanishing here. So that's the MD of rhodochrosite at 750 Kelvin. So the main thing is that if we increase the temperature, the homolume gap between the calcite and different forms of calcite will decrease, so that we can hope that with the increment of temperature we can find the color of calcite or doped form of calcite, because in normal temperature calcite is colorless. But if we increase the temperature, if we find the calcite from very deep in the earth, we can find different colors of calcite. So if we do the simulation at higher temperatures, the homolume gap will decrease, and then we can get some colors of that.
Let's thank Faisal. His presentation is open for discussion. I have one. So you are replacing which ions? Calcium? Out of how many? What is the proportion of your transition metal doping?
There is 6 calcium ions in one unit cell for the geometric structure. So we just replace 1 calcium ion with 1 iron, and 1 calcium ion for the manganese iron for the rhodochrosite.
Can you show next slide?
That's for the rhodochrosite.
Okay. More questions to.
So I saw that the color of this material is changing due to the impurities, right?
Yeah.
Due to the whatever iron or whatever other transition metals you incorporate as a doping.
Yeah.
You call it doping, I would call it impurities. So I kind of completely lost what exactly is the role of temperature and why you so much dealing with temperature for these cases. I don't see that you're changing your band gap when you introduce impurities.
But also in the case of pure calcite, if you do it for the higher temperatures, you can also get some colors, I think, because with the increment of temperature, the homolume gap is moving towards the visible region. So
But do you have a physical reason why the gap is changing when you increase the temperature?
Because you may find calcite in different sedimentary environments, so you can get a 300 feet depth, you can also get in 2000 feet, and if you do much and much deeper, you can get the calcite. And due to this geological pressure and temperature, maybe there will be some form the property change, so that you may get the
But
calcite.
this changes the crystalline structure, right?
Yeah,
But it's still crystalline, right? When you run your simulations at very high temperatures, you're probably losing your crystallinity.
It becomes more amorphous, right? It's completely losing its symmetry. Is it? Like, especially when you go into 1000 kelvins, 700, 800 kelvins, I guess your structure becoming really very soft and not very similar to what you expect
Yeah,
from that other base.
due to the high geological pressure and temperature, it may be possible the calcite may form into aragonite, and from aragonite to betadite. Yeah, there will be some sort of
Have you
difference.
been able to get this specific?
No, I have not done the MD at that much.
So
temperature.
please know that this research was going on only for 2 weeks, and one cannot complete.
Right, but my point is, I
Yeah.
think the decrease in your gap.
It's coming not because like it's not really related. I don't think you can really relate it exactly to this idea that it was formed at this temperature, so that temperatures, that's why its crystalline structure becoming different, the gaps are different. It's just because you really introduce a lot of disorder in your system, right? And you're having a lot of kind of let's say this decrease in the gap coming due to the
Doping or
because you have a lot of disorder in your lattice, right?
Yes? You agree? He agrees. Well, thank myself for presentation and for discussion. And, presentation is by Zachary Gertz. He will be presenting an investigation of the catalytic reaction, so some chemical reaction facilitated by a catalyst.
Okay, hi. So my name is Zach. I'm sure you guys are familiar with me by now. This is good. So today I will be presenting my results on reductive nitrosylation, molecular dynamic simulations. So what is reductive nitrosylation? Well, it is a reaction where nitric oxide gets oxidized to nitrous acid, which then ends up reducing some metals such as iron. And so this process can be thermodynamically modulated depending on pH and other factors that may impact the electrostatics of, let's say, the transition metal. However, my focus will not be on the thermodynamic properties, but rather the rate at which the reaction proceeds based off of dynamics. And in particular, I will be modeling the second step here and the third step. Okay, so why should you care? Well, nitric oxide is a very common cell signaling molecule in many life forms. And its interactions are principally with cofactors that are metallic, so like metalloproteins. So there is some physiological relevance to nitrosylation. What I will be attempting to do with these simulations, I kind of briefly mentioned it, but it's to figure out what the optimal angle of collision is in order for the reaction to proceed. And the molecule that I will be using to exemplify this is this nitrosyl protoporphyrin 9, iron 3, coordinated with imidazole in the presence of hydroxide. Okay, so I performed molecular dynamics using VASP. I also used density functional theory to determine some density of states and calculate the Kantian orbitals. So, a couple things real quick. The spin states in all of my models are singlet, so I don't have higher order spin states. And for the actual molecular dynamic model, it is charge neutral. All right, so this just shows the geometry optimized structure for my first model. The thing to keep in mind is that the HOMO has electron density on the porphyrin ring, whereas the LUMO has electron density on the nitrosyl ligand. If we look at the Sorey transition of this particular model, we see that these transitions are dominated by molecular orbitals that have charge density along the porphyrin ring, the iron-star transitions that are commonly observed in porphyrins. All right, so let's look at a molecular dynamics simulation where the hydroxide kind of grazes by the NO. As you can see, we don't get a reaction. That may not be entirely surprising. But when we look at the electronics, it will differ from the model I had shown you before. So here, our HOMO, we have charge density now on the hydroxide, whereas the LUMO once again has some charge density on the nitrosyl ligand. If we look at our Serre transitions here, while our HOMOs, where the transitions arise from, are delocalized in the porphyrin ring, some of the LUMOs actually have some charge density on the ligands. So there's a slight difference there. Now, when we look at a molecular dynamic simulation where the hydroxide collides directly with the nitrosyl, what we've noticed that, hey, we've not only connected, we've formed a bond, and it's dissociated from the iron. So we formed our nitrous acid. If you recall, with our Serre transitions, so what does that look like electronically? Well, our HOMO has some charge density on the iron center, slightly different from what we've seen before. We have charge density now back on the porphyrin rings for our LUMO. More interestingly is that those were, and the LUMOs partially localized on ligands. It's not anymore, it's back on the porphyrin ring. Another interesting thing is that if you plot energy as a function of time during the molecular dynamic simulations, notice is that there's this huge gap, or drop, I should say, in, say, potential energy or increase in kinetic energy for the direct collision. Intuitively, you would think this may actually correspond to either a bond forming, breaking, or some reorientation of the molecule being a kinetic barrier. However, at these time points, there are no ionic positions or atomic positions that can be related to forming bonds or breaking bonds. All right, so in conclusion, the hydroxide nucleophile here, when it directly collides with the NO, does proceed with the reaction. This is kind of supported that the reaction actually has happened by the reorganization of the electronics between where it did not undergo reaction and when it did. And one could state that the reaction appears to be thermodynamically favorable, but that may be an artifact in how the simulation was ran. And there's plenty of future work one can do with this on a kinetic standpoint or a thermodynamic standpoint. But one would like to relate reductive nitrosylation susceptibility to the iron 2 redox of said proteins.
Okay,
Chris.
let's thank Zach for interesting presentation. The presentation is open for discussion. Any questions? I have one.
Of course.
You are telling that you have iron 3, iron 2.
Mm-hmm. Mm-hmm.
Is it possible, and what would you do to follow the change of the oxidation state of iron at each step of the reaction?
I would look at the partial charge densities of the populated molecular orbitals to see where they are located. So if they are primarily located along the iron center, then that would suggest that there are electrons there in orbitals that reside on the orbitals of the iron. However, one thing I kind of skipped by because of time, and I can quickly educate, is NO is known as a non-innocent ligand. That is to say that it is difficult to discern what the oxidation state is of this iron center. So I may start with an iron 3, but the actual formal oxidation state of that iron can be iron 3 or iron 2, depending on where the pi star anti-bonding electron resides.
Okay. More questions to Zach? If no, let's thank him for detailed answering presentation. And the next presenter is Mendikantila Nakasinka-Dorata. So he will present another mini research related to chemical reactions on the surface, but in contrast to previous speaker, he will look on the reactions catalyzed by solid surfaces rather than molecular catalysts. Okay, floor is yours.
Thank you, Dr. Dimitri. And good afternoon, everyone. So, my study is about catalytic electronic structure dependence on thiophene hydrodesulfurization reaction. So, in petroleum industry, hydrodesulfurization is known as the process of removing sulfur contaminants from natural gas of crude petroleum products to form refined petroleum products. So during this hydrodesulfurization reaction, during this sulfur removing process, the sulfur contaminant hydrocarbon is treated with hydrogen gas in the presence of heterogeneous catalyst at elevated temperatures and pressures to form this refined petroleum products, and hydrogen sulfide is formed as a byproduct. So here you can see a simplified catalytic hydrodesulfurization reaction mechanism in this diagram. So there are several theoretical and experimental studies have been conducted to study this hydrodesulfurization process, and in most of these processes molybdenum surfaces or molybdenum nanoclusters have been used as the catalyst, and thiophene is used as the probe molecule to study this hydrodesulfurization reaction. So the main objectives of this study is to model the hydrodesulfurization reaction of thiophene on molybdenum surface and study the dynamics of this hydrodesulfurization reaction, and also study the catalytic electronic structure dependence on this hydrodesulfurization reaction. So, so in this study, as the model system, a thiophene molecule adsorbed a single crystalline body-centered cubic molybdenum surface with 24 molybdenum atoms in excess hydrogen atmosphere is used, and the electronic structure of this model is determined using density functional theory, which is implemented in WASP software. And also molecular dynamic simulations have been used to study the evolution of the position of atoms during heat treatments. So thiophene seems to be dissociatively adsorbing on catalytic surfaces. So catalytic surface, here you can see the variation of carbon sulfur bond distance during this adsorption process. So as you can see, with time one of these carbon sulfur bonds are dissociating, this bond is elongating and dissociating. So here you can see the carbon sulfur bond distance as a function of total energy. As the carbon sulfur bond distance increases, the total energy of the system decreases. That means the system tends to stabilize by dissociating this carbon sulfur bond. So this movie further illustrates the dissociation of this carbon sulfur bond during this adsorption process. So this further confirms that thiophene is dissociatively adsorbing on these catalytic surfaces. So here also we calculate the binding energy of this thiophene molecule on these neutral molybdenum surfaces, and it is found to be 4.1 electron volts. So if we calculate the binding energy per non-hydrogen atom, it is about 0.83 electron volts, and it suggests that this thiophene molecule is strongly chemisorbed on this molybdenum surface after adsorption. And also our calculated results are in qualitative agreement with experimentally determined data. So then we determined the catalytic electronic structure dependence on this thiophene hydrodesulfurization reaction. So here you can see a thiophene molecule adsorbed neutral molybdenum surface at 0 Kelvin. So at 0 Kelvin, only one carbon sulfur bond is dissociated here, and when the surface temperature is increased to 1000 Kelvin, even though this carbon sulfur bond is elongated, it is not dissociated, it is not completely dissociated. So this movie illustrates the dynamics of this thiophene molecule adsorbed on neutral molybdenum surface at 1000 Kelvin. So at 1000 Kelvin, this one carbon sulfur bond is completely not dissociating. That means this sulfur is not removed from this hydrocarbon, and it is not catalytically active to remove this sulfur contaminant from this hydrocarbon fragment. And we also did, so here you can see thiophene molecule adsorbed on oxidized molybdenum surface moderately oxidized molybdenum surface. So at 0 Kelvin, like in the neutral molybdenum surface, only one carbon sulfur bond is broken. So when the surface temperature is increased to 1000 Kelvin, there are evidences of dissociating both carbon sulfur bonds. That means it seems like catalytically active towards hydrodesulfurization reaction, oxidized molybdenum surfaces. So this move illustrates the dynamics of this thiophene molecule adsorbed on oxidized molybdenum surface, and as you can see, after heating at 1000 Kelvin, this these carbon sulfur bonds are instantaneously dissociated at 1000 Kelvin. That means these oxidized molybdenum surfaces can be used as catalyst for hydrodesulfurization reaction. So as conclusions, thiophene hydrodesulfurization is dependent on the electronic structure of the surface, and neutral surfaces are catalytically inactive towards hydrodesulfurization, and oxidized surfaces are catalytically active towards hydrodesulfurization reaction. And to remove those adsorbed sulfur and hydrocarbon fragment, we may need to further increase the surface temperature.
Okay, let's thank Tivan. And his presentation is open for discussion and questions. Students attending the course are welcome and encouraged to ask. Okay, if there are no questions, I have one. So if you follow your own plan, the last word of your presentation, further increase of temperature to induce desorption of your products. What is your expectation? Which of the products will you desorb first?
Usually sulfur have some high binding energy towards with the molybdenum surfaces. So I am expecting to remove hydrocarbon fragment first. So at lower temperatures than removing sulfur. So removing sulfur is equally energy required step like hydrodesulfurization process. So during hydrodesulfurization, it is equally known as removing sulfur from the surface, and also the carbon sulfur bond dissociation. Both are equally rate determining steps.
Questions?
And I didn't really mention about your methodology, how you know that what functional do you use, what basis sets, and how you know that this will be valid for your system?
Maybe your data are really affected by taking smaller bases. If you increase the bases, you will see that this happens not at bond breaking is happening not at 700, but much lower temperatures.
Do you have any justification of the methodology?
Experimentally, this reaction is done at around 700 Kelvin, 700 Celsius. So that's why we use 1000 Kelvin.
Okay.
Approximately, what is the size of your simulation cell? Approximately, how many nanometers or angstrom?
7 by 7 by 7.
How big is your unit cell? How big is your simulation cell? It is of the order of the thiophene molecule.
It's in the level of angstrom.
But the whole simulation cell, how big is it?
Maybe about 4 to 5 angstroms.
Hmm?
Maybe about 4 to 5 angstroms. I'm not exactly.
Maybe a little bigger.
Yeah.
Okay, let's thank Tivan for a good attempt to answer all questions. And the next presentation continues the subject of catalytic reaction. It is by Brandon Disrot. And I would like to bring to attention that this course was offered to both graduate and undergraduate level students to bring the same level of technical skills and cover broader audience. The floor is yours for generous 4 minutes.
All right, I'm Brendan. I was looking at reaction between carbon nanotubes and hydrogen peroxide. a little bit first on all the different types of carbon nanotubes. They're split up into single-walled and multi-walled, but we're going to be using only single-walled, and only one specifically because single-walled are much smaller. And then there's also a specific vector that is applied to the carbon nanotubes, which describes their shape. The single wall versus multi-wall. Single wall is probably your basic one atom thick, and multi-wall is pretty much like a single wall inside of another single wall, and so on. For the vectors that describe them, you can think of them as a graphene sheet, and then vectors along that graphene sheet point to another carbon that you would roll up into a tube and connect them there. So the three types that we could get when we do this are zigzag, where one of the pairs of vectors is a 0. So I've tried to highlight them in these pictures here so you can kind of get your mind around them. And we're going to be using zigzag, but there's also chiral vectors, where it's 2 unique numbers, and armchair, where both of the pair of vectors are the same. So we use the 4-0 that you saw earlier on the zigzag one, and we expected when we react it with the carbon nanotube or the peroxide that we'd get some formation of epoxides and carbonyls, as well as a burning reaction where carbon is removed from the carbon nanotube to make CO2 gas or something of the like. And this would make a hole on the nanotube. So we looked at this unit cell here, which is 2 units of the carbon nanotube long, and it has 16 hydrogen peroxides around it. And we ran a dynamic simulation for that. And one interesting part here, you can see the reaction between the hydrogen peroxide, one of the pathways here. The hydrogen peroxide breaks and a hydroxyl group goes and forms with the nanotube, which is one of them that I did not expect to happen. And in this still frame here, it's kind of hard to see, but the 6-member ring on the carbon nanotube was functionalized with 3 different oxygens, and it actually broke and created a hole on the nanotube without dissociating a carbon off of the nanotube. I also looked at the system under both cationic and anionic states. The anion is here, and we see more reaction, but nothing like the cationic state where the whole nanotube kind of just breaks apart. And the ionic states we looked at are probably more than you might expect to find in a regular lab experiment, but it will give a good approximation of what we can do with a more limited time. So what we did see was reactions that I didn't expect. First off was the hole with no leaving group. We saw an epoxide form, and it was stable for hundreds of femtoseconds, but ultimately it did go to form a carbonyl. We kind of saw maybe a little bit of the burning with the cationic state, but not really anything like I had expected. And then hydroxylation and hyperoxide formation that I didn't originally expect, but we saw those as well.
Okay, let's thank Brendan for a very interesting presentation. And this study of exotic regimes of reactions is open for discussion.
So I have a question, please. Can you go back to where you have the charged species?
This one?
Which one is which?
Oh, this one's anionic and that one's cationic.
Why is it a cation?
So
How do you create the cation?
Well, the way we did it was artificially removing or adding electrons, but I think the thought is that could model
But
a Lewis
On the
acid-based
molecule,
system.
on each of the molecule, I mean, it's a single
So-
cation or
a unit
what?
cell.
Oh, it's largely ionized, like more than 10 electrons, like 16. 16 out of like 300 or something.
So do you have any rationales between why one broke totally apart and the other one kind of didn't see much?
I think it was, and I looked at it, but it was a while ago. I think more of the electrons, like the change in this one came around in the solvent, and that one it was more on the tube itself.
So, for functionalizing your carbon nanotubes with oxygen, you can like directly use atomic oxygen. Was there a specific reason why you had to use like hydrogen peroxide to functionalize the carbon nanotube surface with oxygen?
That's just what I was looking at. No reason specifically, no.
Okay.
Would you consider this more as a gas phase or more like a liquid phase?
This was probably gas phase because it was very hot, like at 2000 Kelvin, and maybe it could be a liquid at really high density like pressures, but gas.
Okay, let's thank Brendan once again. And the next presentation continues the subject of the electronic properties of functionalized carbon nanotube. And the presenter is Whitney Kong. So she will look more on the electronic structure side of the carbon nanotubes functionalized by oxygen.
Hi, I'm Whitney. So today I'll be talking about the oxygen absorption on single-wall carbon nanotubes. So first off, I will go through the introduction and I'll talk about the motivation of this project, and then I'll talk about the methods, result, and then finally the conclusion. So first off, the introduction. A carbon nanotube is a folded sheet of graphene, a sheet of carbon. Okay. And then some of the applications including electrochemical gas sensors, and they also use in polymers to control and enhance conductivity. They are added to anti-static packaging. So why am I talking? So for gas sensors, it can induce a strong change in conductance, and then the carbon nanotube can be used to detect gases such as NO2 and NH3 or oxygen, and experimental data has shown that oxygen increases conductivity. So we are using computational methods to look at this thing. So I use, to build and edit the models, I use Avogadro, JMOL, and VASView. And when I run the jobs, I use the VAS software. And then I use a 3-unit cell of carbon nanotube folded at 4,0, and I manipulate the position of oxygen on the carbon nanotube. So after optimization, I found out that the bandgap of the modified system definitely decreases compared to the pristine. This one I have one of the carbon substituted with oxygen, and a few other cases where I have just I remove one carbon from the nanotube and just have one oxygen molecule on top of it, and the other one I just put either parallel or perpendicular to it just to look at the result. And the bandgap definitely decreases. And then when we look at the absorption spectra and the molecular orbitals, for the pristine structure, we have the absorption spectra at 0 frequency, but for other systems, they decreases significantly for the absorption spectra. The oxygen definitely decreases the band gap and thus increases the conductivity. The change in absorption spectra also proved that oxygen is present.
Okay, let's thank Whitney for interesting presentation and for being record short, which is very appreciated in our circumstances. And very appreciated in our circumstances. And her presentation is open for discussion.
On one of your tables, you had log of A. What does that mean?
So the A is the absorption at 0 frequency, but because it's too small to measure, so I use logarithm.
More questions?
Could you provide more analysis, like you were putting these different alignment, different positions, right?
And so you're saying, okay, electronic structure is definitely a factor, but this is very trivial result. You can say it without doing any calculations, right?
Yeah,
So you can give a little bit more physical or chemical explanation, like in which case, which one is why this or that, right?
So for sure we can see there's difference like the oxygen definitely affect the density of state.
But when you compare, for example, substitution of oxygen versus just kind of attachment of O2 molecule, his absorption of O2 molecule, right? In both cases, your gap is decreasing, and right. But is it the same nature? Any difference in electronic structure between these two cases somehow?
Not really. I don't think so.
But do you expect it should be different or something should be different?
No, I was hoping to have more time to look at other ones, but I only managed to get this much information result.
But did you take a look on the orbitals localization? Maybe this could give you some ideas, right?
So for the HOMO and LUMO, it does not change a lot except for this one. It has localized orbitals on the oxygen.
In which case, when you substitute or what?
No, the one that I put on top just.
So when it's phase absorbed, then you have very strongly localized orbitals.
And these orbitals introduce this closing or these sites inside the gap, right?
In the other cases, when it's substituted, it's more delocalized over the
surface, although the gap is still changing.
Yeah.
Okay, so you have a different nature of this electronic states. Okay.
Thank you.
Dr. Khan?
So what happened? So for the undoped system, it's a semiconductor, right? With a finite band gap, right? So that's true.
How large is the band gap for undoped system? What is the gap?
Yeah?
Yes,
The
approximately.
energy gap. The energy gap. Yeah, it seems to have a finite band gap.
You mean this gap?
No, here. From here to there.
In the pristine case.
So it's a semiconductor, right?
But
Yeah. Yeah.
what is the size of the gap?
I did not come.
Approximately, like
You can look on your phone, right?
0.1 electron volt, 1 electron volt, 10 electron volt.
2?
Okay,
Yeah.
Around 2 electron volts.
So about 2 electron volts. So what happened when you put some species on top of it?
It decreases.
So the system is still a semiconductor or it become a metal?
It's a semiconductor, but I believe it's a semiconductor.
what does happen to the gap?
It decreases.
But it
Would
still
it-
exists, right? It's not completely going to zero.
Yeah.
Okay,
So it's still a semiconductor.
But then, whether it's a semiconductor or not, it also depends on the position at the Fermi level, right? Right.
Okay.
but you are telling that it is not going to, it doesn't transfer to the metal. It is still a semiconductor.
Yeah.
At least what you found. Okay, but thank Whitney once again. So, we have next speaker is Jabir Abu Mohammed. So please set up your presentation And he continues the description of the electronic structure of nanomaterials, and he will be looking on the interface between metal and semiconductor. We have 4 talks for about 20 minutes.
So I'm gonna talk on the initial state of the metal and metal interface for resistive switching applications. So since the resistive switching is a new thing, some guys. So first, let's start what is actually resistive switching. So if you're gonna start on the electrical, they have a 4-parameter voltage, flux, and current and charge. So if you're going to make a relationship, we got a 3 different circuit, but still they have a one relation between the charge and flux missing until 1971, or in the Dr. Liu Chon, he mathematically derived an equation and formed that maybe there should exist a circuit which is called a memristor, and it's practically prepared in 2008 by HP scientists. So how this actually switching is work? So is the device, if we increase the voltage in a positive direction, the conductivity will increases, and it can keep memory that conductivity. And if we put the reverse bias, it will give you that previous resistance. So we are going to make devices with these properties, but question is why we need these properties. So in one sentence, this recent semiconductor-based technology, it's almost in the theoretical limit. After that, so we need new mechanisms. So it would be the replacement of these devices, and it can be used for like neuromorphic device designs. So to do this one, I consider my models. My models actually, I am considering one titanium oxide layer with one of the metal oxide layer on the top of that to study these properties. I studied this system on the bulbs using methodology. To do that, this one is giving us a pristine only metal oxide layer with the metal, and this one is I replace one titanium with the aluminum in the titanium oxide layer to see how it changed their conductivity. I also study with study the oxygen vacancy, how it changed the conductivity, but I didn't actually complete on this system, so I just work on this too. So first one, this one is giving us a 2D presentation of the orbital, how the electron localized in which part, in which layer, metal oxide layer or in the metal layer. So this one is showing the pristine one, and this one is showing the with the aluminum doped one. First, if you look on this lattice structure, by doping aluminum, the lattice structure is distorted much, but this one almost showing this pristine titanium oxide lattice structure. So in this case, HOMO -1 and HOMO, there was some electron delocalization on the metal part in here, and these are in the LUMO too. But when I dope aluminum, this electron is moved towards the oxide part, and also LUMO, it's also showing the all electron transfer to the LUMO layer. So maybe because of this oxygen, it could introduce a charge transfer in this here. This one is just an orbital showing of these two previous one, as shown in the previous slide. This electron almost on the localized on the metal part. In the LUMO is metal part with oxide layer, but in this case of a doped system, this electron is localized on the metal part also. And this is some kind of other presentation of previous slide. But when I take a dose, it's showing that this one is for pristine and this one is for with the metal dope. In the pristine, it's showing that there have a overlap between the Fermi. This is the Fermi level. This is occupied on the. There are some metal characteristics, but there are some significant, energy difference in the HOMO -1 and HOMO low energy state. But when I put the aluminum dope, it's giving it a more continuous orbital occupations, and also the overlapping of the unoccupied by electron is higher of than the undoped system. And these two, I optimize by using the electric field towards the Z direction. Z direction means from here is the metal part to the, metal oxide to the metal directions. In that case, I saw that this one in the undoped system, by applying the electric field, it didn't change the energy level that much. But when in this doping system, it increased the occupation of the unoccupied orbitals with the electrons. Excited electron is much more than compared to this one. So from this advanced calculation, I can say that this one is that because of doping, under the electric field, it changed the occupation number is huge. So doping change can reduce the change significantly, but most important result is that doping have to increase the conductivity by minimizing the energy gap and increase the occupation number in the higher steady state. So, but I didn't do much work, so there are some feature work I need to develop videos and those.
Okay, let's thank Javed for interesting presentation. Questions?
Can I see?
Presentation? Questions?
Can I see the supercell model again?
This one?
I mean, a lot of disorder, yeah. So what happened? Do you think that's reasonable? Maybe the number of layers that you have maybe is not large enough, or you see exactly what you want. So you want to have a stable some bulk-like layer, or you want everything
No, I want a stable one layer, and which will increase the conductivity if I apply the, which will change the resistivity if I apply the current. So that's my.
So you're trying to model more like a thin film, right?
Yeah.
Right. So I could assume that with a thin film you have a bulk-like region, right? Inside the thin film it should be like in a bulk system, right? And near the surface you may have surface reconstruction, surface relaxation, or whatever, right? So it seems that your system is not, good enough to see that. Another thing that you can do is, in addition to adding some more layer, you fix the middle layer. So at least, 3 layers in the middle, fix them at the bulk lattice constant, right? So in order to mimic the bulk layer in the thin film, right?
So my another aim is actually to minimize these device sizes. So if I want to make another layer, it will mimic the bulk sizes, but I want to make a smaller device. So, 2D device, one layer.
Okay, so you want very thin.
So then I can make a bigger number, many number of devices in small pieces. That's also important.
Have you considered tunneling?
Yeah, I have to. So I cannot make it as more smaller. So that's why I need to optimize.
But is this big enough?
I want to minimize tunneling because if I get the more tunneling, it will become a conductor. So we need to optimize tunneling and Scott cubic barrier too.
Okay, but we should be short.
How do you incorporate electric field into your system?
In bulks, there have this one, but do you want methodology? How do you use this one, or
Okay, so
how do you calculate this one?
There's a strict methodology that you have to follow.
Yeah.
Is that in your this?
Yeah. No, I didn't include that one here.
Sounds good.
But I do have. I can if you want.
Okay, let's thank Javed once again.
Sure.
And we have